Hello folks and welcome back to ECMath. Today we're going to talk about section 322, which is the graphs of logarithmic functions. So previously we've practiced just evaluating single logs, log base 2 of 8 or things like that, but we haven't really viewed logarithms as a function themselves. But if you think about what log is, you have an input, the argument, and you have an output. So we could think about this as a function where we just have an input x and that gives us some output y. And if we think about it as a function, then it should have a graph. So let's see if we can figure out what it would be. By way of introduction, we're just going to start by plotting points. Now, this is not how you're going to graph logs generally, but as we work up to it, let's start here. I challenge you to on your own pause the video and plot some points on your own and see if you can think about what the graph might look like, and then come back if you want to see what it actually looks like. All right, so let's start with the table here, and I've left some spaces out. We'll fill those in as we go. But let's start with -1. So this would be log base 2 of -1. Now I want to think about this for a second. That would be saying 2 to the what equals -1. There's no such value. So this is not defined. I'm going to say undefined at -1. All right, let's try 0. So this would be log base 2 of 0. That's a 0. Which is saying 2 to the 0 equals what? I'm sorry, I've actually made a mistake, but I'm going to leave that in instead of cutting it out. This is saying 2 to the what equals 0. Remember, when you're switching log form, that can be one of the easiest places to make a mistake. Is there any power of 2 that will actually make 0? No. So 0 is also undefined here. Okay, let's keep going. I'm going to skip over this space and go to 1. So this is log base 2 of 1. That's saying 2 to the what equals 1. Now we have an answer. 2 to the 0 equals 1. So I put 1, 0, because log base 2 of 1 is equal to 0. So now we're starting to get values. Let's keep going. So 2, so log base 2 of 2 is saying 2 to the what is 2. That's 1. There we get the 1. Okay. So now I have 2 points, 1, 0, and 2, 1. Well, that's not bad. So I have 1, 0, and 2, 1. And I have some undefined values over here. We'll just do like x for undefined. And maybe even x to say, hey, I'm undefined on that axis too, right? But I want to get some more values, because at this point, 2 points doesn't really make a line. I don't know what's going on. So I want to think about what I could put in the x table to get good numbers. Well, if I do 3 here, then I'm doing log base 2 of 3. Is that a number? Yes. Is it a number that I know will go nicely on the graph? No, because log base 3 is not an even power of 2, right? 2 to the what equals 3? I don't know. It's something, but I don't know what it is. So instead, when we're making our x table for logs, you want to be smart and think about things that are like nice powers of 2, like maybe 4, because log base 2 of 4 is saying 2 to the what equals 4? Well, that's 2. And we can go one more. What about 8? Because log base 2 of 8 is saying 2 to the what is 8? That's 3. So now we're starting to get good actual kind of whole number values. You have to be smart about your x table to get good numbers in your y table. So let's go to 4, 2, and 8, 3. And the next point would be 16, 4. That doesn't seem like it's going to fit on my screen, so I think we'll stop here. So we can start to connect these. And we see that log graph is a graph, I missed that point, we're just going to pretend, is a graph that's starting to grow very slowly, but it is growing. And if we went out to 16.3, right, it would just continue to grow. It will always grow, but it will always grow at a slower and slower rate. It never has a horizontal asymptote. It never has a cap. But it will always just grow at a slower and slower rate as time goes on. I've even drawn that a little too linear. It should really start to curve like this. But it never caps out. Okay, so this is almost a complete graph of log base 2, but we have missed a really important spot in the graph. And it's the spot between 0 and 1. Remember, when we graph things, we're not just graphing whole number values. We need to think about all possible fractional values also. So we got to think about what's going on in here. Is it undefined? Maybe. Does it have a value? Maybe. We have to plug something in and actually find out. I'm going to plug in 1/2. So that was that missing spot there for 1/2. So if we want to compute log base 2 of 1/2, that's saying 2 to the what equals 1/2. Well, since 1/2 is 2 to the negative 1, then log base 2 of 1/2 is -1. So we do get a value there, and in fact we get the value 1/2 -1. And if we did more points with the fractions that have powers of 2, we'd start to get more and more negative values. I'm not going to put them in the table, but I'll just put them on the graph. We have 1/4 -2, 1/8 -3, and so on. And so what's happening with this log graph is, even though it's undefined at 0, as x approaches 0, I'm going to do that in blue. As x approaches 0, the graph goes down to -infinity, and you have a vertical asymptote at x equals 0. So the log graph has unrestricted but slow growth to the right and a vertical asymptote to the left. And this is the graph of log base 2 of x. So the base, of course, won't always be 2. So let's look at the general features of sort of the parent graph for just log base b of x, whatever that base might be, because they have a lot of the same similarities. So the key points on log base b are 1, 0, because log base b of 1 is always equal to 0 no matter what b is, and b 1, because log base b of b equals 1. So those are the two key points. And then if you need a third key point, the next point would be b squared 2. Because it is true that log base b of b squared is always equal to 2 by one of the properties, the inverse property that we looked at earlier. So here I don't know what b is, but I know, okay, I know we have 1, 0. And then I'm just going to assume that this is, I'm going to mark that as b. And then we would have the point b1. And we'll just say that that's b squared 2. And I also know that I would have the point 1 over b -1. Let's add that to the list of key points. Because it's nice to remind ourselves that we have that fractional values too. The other important feature of all log graphs, no matter what the base, is the vertical asymptote at x equals 0. Every single one of those has them. They also have no horizontal asymptote. Only that one vertical asymptote. So I'll draw that with a squiggly purple line. And with the key points in the asymptote, we can now sketch the graph. It looks just like the one of log base 2, but goes through slightly different points. So I like to start at -infinity, go up, hit my 0, 1 point, and then turn over and come out. Make sure you include arrows on both ends to show what's going on. We can talk about the end behavior. It's not like a rational function where there's an end behavior test, but we can still describe the end behavior. Oh, no, not like that. So we can describe the right end by saying, as x goes to infinity, f of x goes to, well, in this case, we said it goes up without bound, so it also goes to infinity. It's just very slow, but this log graph will eventually go as far up as you want. And as x approaches 0 from the right, we say f of x approaches -infinity. That's because the left end is not at -infinity. The left end is at that vertical asymptote right there. So that's its kind of end behavior in those two ways. You could also do this in limit notation if you know what that is. Same deal. What is the domain of this graph? The domain is x greater than 0, but not equal to 0. And the range is all real numbers. Because it does go all the way down to negative infinity down here. And this green arrow, as it goes off the page, would eventually reach any positive value. So it's still going to go to positive infinity. Eventually, it just will take a very long time. Now, when you're sketching a graph of log, you don't always have time to plot every single point. So here's the 3 things that you should include in every graph of log. You should include the asymptote, vertical asymptote. You should include that intercept, and you should include one other point. Those 3 are like the critical values. Other things can help you see the shape if you're not sure what's going on, but those are the 3 things that you should have in every graph of log, no matter what base you have. So we kind of have been hinting at this idea that logarithms and exponents are inverses of each other, that they undo each other. And we saw this in the last section when we talked about the inverse properties. Those were the properties of logs that looked like this. Log base b of x, b of b to the x is x, and b to the log base b of x is also equal to x. And we justified those before by just rearranging them into an alternate form. But if you think about the log function, log base b of x as f of x, and b to the x as g of x, then what we've really done here is actually a composition of 2 functions. We've done here f of g of x, and here we've done g of f of x. And both times we got back x. And that implies, at least, that f and g are inverses of each other, using the language of functions. So, well, what's the inverse? So you're saying that log base b and b to the x are related through being inverse functions. Okay. Let's try to find the inverse of an exponential function. We're going to start with something we know and see what happens. So do you remember the steps for solving for inverses? The first step is we switch x and y. So then in y equals 2 to the x, it becomes x equals 2 to the y, which I think you may have graphed on a previous homework assignment. Then we have to solve for y again. Well, we can't take like the yth root of this, but what we can do is turn this into log form. We have log base 2 of x equals the exponent y. We're putting this into log form. And, well, we solved for y. We actually now fully solved for y. This is done, which means y equals 2 to the x and y equals log base 2 of x are inverses of each other. And if we go back to the problem we started with, where we graphed log base 2 of x, let's take a look at the table. Where did it go? If you were to instead label this table, so we had x log base 2 of x as x and 2 to the x, and read the table backwards, those would be the exact same values of x and 2 to the x, right? 4 to the 2 is 16, 3 to the 2 is 8, 2 to the 2 is 4, and so forth. So that's like one way to think about inverses, is reading the table backwards. If you remember from when we talked about inverses before, it also means that the graphs have a very particular relationship. Specifically, the graphs are reflections of each other over the line y equals x. And the reason that is because when you switch x with y, that causes this reflection. So here's the graph of 2 to the x. And I've drawn it with its horizontal asymptote to show you that the asymptote also gets reflected. Here's the graph of log base 2 of x that we graphed earlier. There it is. And so you can see that everything in those graphs gets just reflected. You're switching y with x, including, like, right, when we had asymptote y equals 0, this one has asymptote x equals 0. One word of advice or caution, I should say at this point, is sometimes folks will see this slide and then they'll think to themselves, aha, What Mr. Eck is saying is that I don't need to learn the graph of log because I already know the graph of exponential functions and I can just reflect them. You need to learn the graph of log. Because this approach of inverses works and reflections works well before we bring in the idea of transformations. This is really nice with the parent functions, and it still technically works with transformations, but it's much harder to execute than just learning how to transform the graphs of logs themselves. So even though they are related to the graphs of exponential functions, I expect you to treat the graphs of logs as their own sort of parent function that you, independently of exponential functions, know everything about their graph and you know how to graph. Speaking of transformations, here is a quick review of the order of transformations. So if we have the equation y equals a log bx minus c plus d, and by the way here this can be any base. I've written just log because I didn't want to make it too much alphabet soup. So a, b, c, and d just stand for like different sort of coefficients. The order of transformations is a horizontal shift by c, horizontal stretching and shrinking, horizontal reflecting, both whether if that b is negative, then you go vertical stretch shrink by the factor of a, vertical reflection if you have a negative a, and a vertical shift by d. So those are the 6, and they have to happen in that order to get the correct graph. When you're graphing logs, always graph for me 2 or more key points and the asymptote. So at the very least, an asymptote and 2 points, maybe more. The specific points will depend on the base that you have, but the general base is the same. And in the rest of the examples, we're going to mix up the bases so you get a chance to see what that looks like. And always remember that when you shift things around, you have to transform the asymptote as well. So if you're shifting left and right, don't just shift the points, also shift the asymptote. We're going to see that in just a minute. So for the first log graph, let's take a look at log base 3 of x plus 3 minus 2. So what are the transformations happening? Well, we do the input transformations first, and this is going to be a shift left 3. There's no other input transformations. There's nothing in the out front. So the only other transformation that we're going to do is down 2. So also make note, we're looking at a base of 3. That's going to affect how we sketch our parent. Let's go ahead and sketch that parent graph right now. So the parent graph has a vertical asymptote at x equals 0. It goes through 0, 1. I got that backwards. 1, 0. And 3, 1. Because it's a base of 3. And it has that characteristic log shape with the vertical asymptote at 0. Now let's take all of these features and shift them left 3. So including the vertical asymptote, we go left 3. Remember that an x plus 3 causes a shift to the left. We've talked about that before. It's the same with logs as it is with everything else. Once I have the vertical asymptote, I'm sort of copying the relationships of those 2 key points. So all of those 3 points will move over, or 2 points will move over 3, and the graph will have the same shape. Then we'll shift all of those points down 2. So the asymptote doesn't have to move anymore, but the key points go down 2, 1, 2, 1, 2, and we can go up like this. And I actually, as I go, I want to put one more point on the graph now that I see that I've shifted down 2. On the parent graph, we would also have the point 9, 2. And that would go then, in this second graph, it would go over 3, 1, 2, 3, so that would be over here. And in a green graph, why did I want to do that? Well, if I shift that down 2, I get right to 0. So in this graph, we have, if I drew it right, there we go. We have a nice x-intercept. So that's nice to see. Not required, of course, but nice to see that we have a 0, 6. Now, let's did it again. 6, 0 as a nice, convenient x-intercept to find. Make that go down a little more. So this would be our example of a transformed log graph shifted over and then down with that log shape. All right, next we have negative ln of negative x. And a lot of folks are kind of scared of natural log. There's no reason to be scared of natural log. So the first thing to remember is this is the same as negative log base e of negative x. So we have a base of e, and the only thing that affects is the key points in the parent function. So in the parent function, we still have the vertical asymptote at x equals 0. We go through 0, 1, 0, and instead of 2, 1 or 3, 1, we go through E1. That's it. That's the only difference. And over here we'd be at 1 over E, negative 1. That's the only difference in the graph of natural log x compared to any other graph of any other log, is that e is the first point, which is, again, roughly 2.7, but there's nothing to be afraid of. All right, so what are we doing with the transformations? Well, we have a double reflection here. So this is going to cause us to reflect over y, and then this one will cause us to reflect over x. So let's carry those out. So first reflect over y. You can technically do these in either order. When you reflect over y, the points and their relationships will stay the same, but you're now opening to the left instead of to the right. And then when you reflect over x, we're going to take those same values and go over the x-axis. So this point will be down here. This point will be up here. The point at 0 will stay. And the vertical asymptote is going to stay. But our behavior will be more like increasing as we go towards that vertical asymptote. Increasing up. And we have really slow decreasing growth to the side. So that's the resulting graph after two reflections. One point of contrast here, if you were looking at this graph, from a distance, you might easily mistake this for exponential growth because it has that sort of curve going up. But exponential growth does not have a vertical asymptote at all. This is growth, but it's not exponential growth. It's like reflected logarithmic growth, I guess. But it's, we have that vertical asymptote, and then the function is just entirely undefined over on the right side. So be really careful, thinking about the kinds of growth, and make sure you look at the function as you go. All right, let's do another graph. All right, so we're now looking at the graph of y equals 2 log base 5 of negative x minus 1. Our base here is 5. Let's go ahead and sketch the parent of just log base 5. So we still have x equals 0 vertical asymptote. We still have 1, 0 as the point. And now we're going to go all the way over to 2, 3, 4, 5, 1 as the second key point. And over here we'd be at 1/5, negative 1. So this is our parent graph for log base 5. Log base 5, to get all the way up to 2, it's going to be very flat because we have to go all the way out to 25 to even get up to 2 on the axis. So this is a good place to stop log base 5. Now let's look at our 3 transformations. This is an example of the dreaded double x transformation that we always struggle with. So in this case, we're going to have to be really careful about the order. First, we said we are going to shift right 1 unit. Then we're going to, in this order, reflect over y. And then we deal with the output transformations. We're going to vertically stretch by a factor of 2. So 3 transformations in this order. Here we go. So shifting this graph right 1, we have to shift the vertical asymptote as well as every key point. Okay, something like this. I'm going to draw it as solid lines, and I think it'll be easier to draw. Now we're going to reflect over y. So reflecting over y, remember that we have to reflect everything over y. A lot of people seem to want to reflect over the asymptote, but the asymptote's not at y equals 0. So we have to reflect over the y-axis. So we're going to take the asymptote, which is at 1, and move that to -1. That's our vertical asymptote. This point was at 2, so that's going to go to -2. This point was now at 6 after being transformed, so that's going to go to -6. So the reflection over y is going to put us into the third and second quadrants instead of the first and fourth quadrants. Now we have to do this vertical stretch. So for the vertical stretch, it's really critical that you've got some key points listed that aren't on the axis so you can actually show this stretch. So here we're at 1 to then carry out the vertical stretch. I'm going to do that in gold. We can go up to 2. This doesn't stretch. This point that was at 1/5 would go down if we had been carrying that through. So the vertical stretch is going to make this graph a little bit steeper as it goes. The key thing there is the order of the right one and reflection over y. Again, if we'd reflected first and then moved right one, we'd be in the wrong quadrant right now. We'd have the right shape, but we'd be in the wrong quadrant. So it is important that we do those things in the listed, or the order that's listed. All right, here's a fun one. It's only a single transformation, but it's one of these tricky ones. It's, again, one of these dreaded input transformations. So we have log base 2 of 1/2 x. And remember that when we have a coefficient on x, we're actually going to divide all the x values by 1/2, which is the same as multiplying by 2 to all the x values. So this is actually a horizontal stretch by a factor of 2 of this log graph. Luckily, that's the only transformation that's going on. So first, we'll draw the vertical asymptote. We'll plot the key points 1, 0, 2, 1, and with 2, it's easy enough to go up to 4, 2. So we'll plot those key points right here. That's our log base 2. To horizontally stretch by a factor of 2, you take every x value and double it. So this point was at 1, that's going to go to 2. This point was at 2, that's got to go to 4. This point was at 4, that goes to 8. This point was at 1/2, that goes to 1. And so on. So we are horizontally stretching every value on the graph to go over that way. A really interesting thing has also happened with this graph, and I don't know if anyone has caught on to it, but it also sort of appears that it's got the same shape but almost shifted down by 1. Right? We actually we didn't shift it down by 1, but it sort of looks like we kind of did. How could that make sense? Well, check this out. We know, do you remember the log rule that went like this? Log of mn is equal to log m plus log n, no matter what the base is. Well, don't we kind of have that here? We have log base 2 of 1/2 x. So by using this rule, we could say, hey, this is equivalent to log base 2 of 1/2 plus log base 2 of x. Now, is there any good reason to do that? Yeah. Log base 2 of 1/2 is equal to -1. So this is the same as log base 2 of x minus 1. That is, log base 2 of x shifted down by 1. And if you took that parent graph and shifted it down by 1, you'd actually produce the same result as a horizontal stretch by a factor of 2. That's really, to me, quite remarkable. We've seen this before with other graphs. For example, if we had the square root of 4x, that's a horizontal squish, a horizontal shrink But just by the power of algebra, that's the same as 2 square root of x, a vertical stretch. But with that, that's just like basically a shrink one way turning into a stretch the other way. Here we actually have a shrink turning into a shift. And that's unique to log and exponent graphs, and it's because of the way that log and exponent rules work. So I just think that's cool. That's one of the nifty features of logs. So to close us out, I want to do sort of a scrambling of the idea of inverse function. So this is a problem that you might see. It says find then graph the inverse function of y equals 3 to the x plus 1 minus 4. So the first move will be to actually construct the inverse. Now we suspect that the inverse will be log base 3 of something. Here's a trap that students often fall into. They say, oh, I know the inverse is log base 3. So they say it's log base 3 of x plus 1 minus 4. Guess what? It's not the inverse. We actually have to go through the procedure. We can't just switch it blindly. We actually have to switch using the procedure for finding an inverse. So the first thing we'll do is switch y with x. And then we have to solve this for y. So we're going to add 4. Now we can convert to log base 3. So it becomes log base 3 of x plus 4 equals y plus 1. And then we'll take away 1. So log base 3 of x plus 4 minus 1 equals y. And that is, f inverse of x for the original function. So compare that to what I crossed out earlier. Notice that it's not the same. All right, so we've found the inverse function. Well, now it's just a shift and a transformation of a log graph. At this point, hopefully we're pretty good at that. Log base 3 looks like this. Plus 4 means we go 4 to the left. 1, 2, 3, 4. New vertical asymptote. New relationships between the points. And then we shift everything down 1. And that would be our graph of f inverse of x for the original function. So that's how, if you are going to relate logs and graphs, logs to their inverse exponential graphs, that's how you do it. You actually need to make sure you're graphing the real original one. Or I should say you're correctly constructing the inverse and graphing that based on the correct original function, not just switching things around. Well, and that's all I have for you today, folks. So we've looked at the graphs of logarithms, we've looked at some key points, and we've looked again at the order of transformations. Hopefully that helps you complete your math problems. Let me know what questions you have, and I will see you all next time. Thank you.